In this session, I am going to explore about the resonance in a series RLC circuit. Resonance in series RLC circuit. Okay, so in this concept, what we are going to find here is the resonance frequency, quality factor, bandwidth of this series RLC circuit we are going to find. So for that, let me consider a series RLC circuit which consists resistance, inductance and capacitance which are connected in series as shown in figure. So this is series RLC circuit which was supplied with some voltage V is equal to Vm sin omega t, right, and this is the resistance, inductance, capacitance. Whenever we are applying some voltage for it, current will circulate in this loop. So this current will circulate like this. So this current, let us assume it is I. Whenever this current is flowing in this direction, there will be some voltage drop across the resistance, inductance and capacitance. Let us consider the voltage across this inductance is VR and the voltage across the resistance is VR, voltage across the inductance is VL and the voltage across the capacitance is VC. Alright, now what is the definition of resonance? It is a phenomenon in which the reactive components of the impedance or admittance should get cancelled. That means I need to write the impedance for the series RLC circuit. Z is equal to R plus J into XL minus XC is the impedance offered by this series RLC circuit. Under resonance condition, this impedance should not have any reactive part. Means it should get cancelled. That means XL and XC should get cancelled. That means XL minus XC should be equal to 0. So that this impedance offers only the real part, that is Z is equal to R under resonance condition. So if we equate this XL minus XC is equal to 0, from this we can get the resonance frequency. Now XL minus XC is equal to 0. XL is nothing but omega L 1 by omega C, that is equal to 0 here. Now this omega L is equal to 1 by omega C. So if I cross multiply it, omega square is equal to 1 by LC. Omega is equal to 1 by root LC. Since we need to differentiate the normal frequency with the resonance frequency, we are indicating it with omega naught. This omega naught is the resonance frequency in radians per second. This is the resonance frequency where omega naught is the resonance frequency in radians per second. And we know that omega is equal to 2 pi f. If it is the resonance frequency, omega naught is equal to 2 pi f naught. And if you want to find the resonance frequency in terms of hertz, that is f naught is equal to omega naught divided by 2 pi. Omega naught we already know that it is 1 by root LC. So if we combine it, 1 by 2 pi into root LC. It is in hertz. So this is the resonance frequency in radians per second, and f naught is equal to resonance frequency that is equal to in hertz 1 by 2 pi root LC. It is in hertz. So this is the formula for finding the resonance frequency of a series RLC circuit. Now let me derive some conditions here. Under resonance condition, we know that under resonance XL is equal to XC. This is the first condition. Inductive reactance, if it equals to capacitive reactance, then there will exist a resonance in case of series RLC circuit. Now if it is XL is equal to XC, then what is the impedance? Z is equal to, actually it is R plus J into XL minus XC. If XL is equal to XC, this Z is equal to R. That means it is the minimum value of the impedance, that is Z minimum. And what is the current? I is equal to, actually it is V divided by Z. Now what is this V? V is the source voltage. If it is IRMS value, IRMS is equal to VRMS divided by Z. And VRMS, we know that it is Vm by root 2, that we already know that. So normally IRMS can be represented with the help of I. VRMS we can represent with the value of, with the representation of V. And Z here is, it is the minimum value under resonance condition, and the value of that Z here is Z minimum is equal to R. So since it is a minimum value, it is the maximum value. So under resonance condition, this current will be maximum, impedance will be minimum. This is I maximum is equal to V by R, Z minimum is equal to R, and XL is equal to XC. Another condition here, if XL is equal to XC, if I multiply with I in both sides of this equation, I into XL is equal to I into XC. So I into XL is nothing but it is the voltage across the inductor, that is VL. So VL, and I into XC is nothing but the voltage across the capacitor, that is VC. That means under resonance condition, this VL is equal to VC. And also let me draw the phasor diagram here. Phasor diagram for a series RLC circuit under resonance condition. I want to draw the phasor diagram. So phasor diagram, which indicates the total supply voltage. This is the total supply voltage V, and the current I, the voltage VR, the voltage across resistance VR, VL and VC. I am going to represent in a phasor diagram. Okay. So here this current is common in all the elements, so that I am taking this current as a reference. So the first vector I am going to draw here, I is taken as a reference. So this is I. Now in a pure resistor, the voltage across the resistor and the current flowing through the resistor is in phase. For a pure, if you consider a pure resistor, the voltage across the resistance and the current flowing through that resistance are in phase. Means this VR and this I are in phase. Now coming to this inductance, the current flowing through the inductor lags the voltage across the inductor by an angle 90 degrees. The current in a pure inductor, the current lags behind the voltage by an angle 90 degrees.